Good morning, everyone. I'm Sebastian Jourdain, a distinguished engineer at Kitware, and with me is Corey Quammen, the technical lead behind ParaView. During the webinar, I will be monitoring your questions and interrupt Corey from time to time to go over those. Since you can ask questions, we also have some polls for you and some questions throughout the webinar. Today's webinar is about microworkflows for making advanced simulation tool more accessible and impactful. So the questions are on the top right of your interface, and feel free to ask them at any time. And like I said, I will take the time to interrupt Corey when it's appropriate. As we wait for everyone to settle in, I'd like to give you a brief introduction to Kitware. Kitware is a leading provider of software and AI research and development services, working with customers and in government, industry, academia, in the area of computer vision, medical computing, scientific computing, and high-performance software solutions. Our mission is to develop innovative software tools that empower researchers, clinicians, and industry professionals. Our team consists of over 200 employees across 6 offices in the United States and in Europe, with locations in New York, North Carolina, New Mexico, Virginia, and Lyon in France. One of the core principles of Kitware is our commitment to open source. Our software solutions are built on vibrant, enduring platforms like ParaView, Trame, and 3D Slicer that foster collaborations and innovation. We strongly support open source science, ensuring that our technology is accessible and beneficial to the broader research and development community. These foundations of innovation, expertise, and collaboration is what drives our work and enables us to develop software solutions like the 3D Slicer software that we'll build, that we've been discussing in the previous weeks, and today a solution like Trames for building microworkflow around ParaView and PTK. Our reputation is built on deep expertise, with 65% of our staff holding a graduate degree. We maintain strong academic collaborations and commitments for advancing knowledge in our fields. Next slide, Corey. Kitware leads the development of a wide range of powerful tools that serve diverse fields, including medical imaging, scientific visualization, artificial intelligence, and high-performance computing. Some of the key platforms we have developed and actively maintain includes CMake, a widely used build system that simplifies software compilations and management, VTK and ParaView, industry-leading visualization tools for 3D data analysis and scientific computing, Pulse Physiology Engine, a tool for simulating human physiology used in healthcare training and research, Viame and Quiver, advanced computer visions and machine learning platform for automated video and image analysis, and many more open source tools. These open source platforms are widely adopted by researchers, government agencies, and industry professionals worldwide. By fostering a strong community and collaboration around open source software, we empower users to extend and build upon our technology, accelerating progress in scientific discovery and real-world applications. Next slide, please. Our speaker today is Corey Quammen, a technical lead at Kitware. Corey, take it away.
Thanks, Seb. That was a great introduction. It gives me great pleasure to be here today to talk to you about micro workflows. I'll probably say that so many times you'll be sick of it by the end, but you'll definitely know what they are and the benefits, why you might want to provide them. The talk I'm about to give is a pretty close version to the talk I gave this past January at the AIAA SciTech 2025 Forum in Orlando, Florida. That there's a publication associated with this presentation called Improving Usability and Broadening Adoption of Simulation with Microworkflows. This is a joint work from 6 of us at Kitware, including Sebastian, who you already know, and myself, David Thompson, Bob O'Bara, Berke Vecchi, and Patrick O'Leary. So with that, let's cover the organization of the rest of this talk. As usual, I'll start with a motivation for why we are advocating for micro workflows and develop them regularly in our course of work. Define micro workflows, and we'll give some examples of micro workflow applications, one of which is Peacock 2.0, which exposes the Moose scientific computation framework, and then ArrowFlow, which is built to make interfacing with MStar CFDs, Lattice Boltzmann GPU accelerated solver faster. Then I'll end with some outlook and future directions of where we see micro workflows going. Oops, sorry. So why are we talking about micro workflows? Well, in modern day and age, a lot of people are using advanced modeling and simulation of products that they develop which can lead to faster time to market, cost savings over testing physical prototypes, and ultimately, through all this cost savings and faster iteration, we hopefully produce more superior products in the end. But there are barriers to adoption. The complexity of the general purpose simulation codes that are available for this purpose is one barrier. It takes a while to use them, learn them, and set them up. There are some large initial and recurring costs, so things like software installation, recurring licensing fees, training for people on how to use them, are some of those costs. And then you can't get away from requiring in-house expertise of people who are versed in not only modeling and simulation, but the physics or electronics or other fields that the modeling and simulation is actually simulating. Need the in-house expertise to set up the simulation workflows, set up the problems, and execute simulations, verify that results are reasonable, and process those results in the end. So often it can be the case that people lean on those in-house experts to do all the simulation work, which unfortunately is not scalable across an organization. So there are lots of reasons that we want to make modeling and simulation easier for more people to use. So in our day-to-day work, we have a couple of goals that drive us. One is to improve usability. So in this case, for modeling and simulation, we really just want to expose what is really needed in terms of parameters, dials to tweak, physical parameters to set, just the very basic minimal set of those things exposed to an end user. And we really want to hide those difficult parts of setting up a whole modeling and simulation workflow from these end users who really just need to know what's going to happen when they, say, change a temperature or a mixing rate in a bioreactor and see what the end result will be. They don't necessarily need to know all the math, the modeling and physics behind it. Just want to make things easier to use for people. The second goal is that we want to broaden adoption of the simulation technologies, make them accessible across an enterprise or research organization. So we still need those computational science engineers to handle the hard parts and set everything up. But again, they're going to be in the business of hiding the parts that non-expert stakeholders don't really care about. And this should enable the non-expert stakeholders to run simulations, change the things that they care about and know about, and then use the results to inform decision-making in the ultimate product manufacture or the ultimate product manufacturing execution. And by broadening the adoption of simulation technologies, we expect that will help maximize the benefit of all these investments that have been made into the modeling and simulation ecosystem, such as If you have a floating license that you paid for, you want to maximize that and be using the software as much as possible to get really maximize your return on investment. So that brings me to our first poll question, and I'm going to set this up here. Give me 1 second, and let's see how this works. So the first question is, what barriers do you face in your organization to wider simulation adoption? And I'm going to launch the poll. Somewhere in your go-to, there'll be a way to answer this. Give you, say 20 seconds. I see some responses coming in here. This is multiple choice, so you can pick more than one. Surely you run into a number of barriers. And we'll give maybe 10 more seconds or so. By the way, we'll have 2 more poll questions after this. Let's see, 78% of folks have voted. All right, looks like it's stabilizing. So I'm gonna end the poll and share the results. So let's see. I'm not sure where the results are shown, but I see them on my screen. And I think the number one barrier to barrier to wider simulation adoption is the steep learning curve. So we've got 57% of respondents say that, followed by cumbersome to use, 43%. Processing the results is difficult at 43%. And then tied at 29% are high simulation license cost and difficult to access the systems that have the simulation software. All right, yeah, so thanks for your input on there. That's interesting to know and confirms what we suspect. Seb, do we have any questions at this point?
Not yet.
Okay.
But they were able to see the result as well. That was one of the feedback.
Perfect. All right, thanks for that feedback. Appreciate it. So I'll continue on then. So if you're in modeling and simulation, you probably know the term workflow. Workflows are used all over the place, but in this case, a workflow generically is just a set of steps to carry out a process, and there's usually some dependence that exists between the steps. So you have to do one and then the other, one before you can do the other. And then modeling and simulation, there can be many steps involved. And each of those steps can require the use of complex software. So the learning curve for each of the steps might be high. There might be peculiarities of the software and tips and tricks you need to know to how to use them. And they can be complex to configure and ultimately use. Here is an example of one kind of workflow where we'll look at some of the actual steps involved. So at step number 1 involves defining the experiment. What are we trying to find out? Are we trying to do a sensitivity analysis? We're trying to optimize a shape to reduce wind resistance or something like that. Setting up that experiment that involves communication between the computational science engineer and stakeholders who want to know the answers to the questions they're trying to answer. Next involves step 2 here in the green. You've got to set up a domain to run the simulation. Often this involves using some kind of computer-aided design, like CAD models, some way to represent geometry involved, placement of maybe chemical reactants or biological agents, and so on. And step 3, you usually have to describe the simulation that you want to run. Which physics? What kind of boundary conditions are there? What kind of Reynolds number does the fluid have? Those all go into a file or maybe a collection of files that are used as input to the simulation that you're running. Step 4 is often required. We have to go ahead and discretize this domain that you've defined through CAD modeling or some other means. It depends on exactly what kind of simulation that you're using, but that's a pretty common and often very difficult step, creating a mesh from the input data. Once all that's set up, you execute the simulation, whether that's on a desktop system or an HPC system, maybe somewhere in the cloud these days. through either a command line, some job queuing system, a batch script, or maybe even within a Jupyter notebook session. Once the results are gathered, then there's post-processing involved where you analyze the data, perhaps produce some visualization to gain some insight in the simulated phenomena, or compute some statistics of interest. Of course, there are many different kinds of workflows. This just gives you it's trying to set the stage for exactly what we're talking about when we're talking about simulation workflows and workflow components. So looking at that, a couple of questions arise that we want to answer. So how do we reduce the complexity involved in carrying out one of these simulation workflows? The last one we saw had 6 steps. Each one of those might take a day or 2 to figure out or to set up. How do we make it easier to learn how to configure those components of a workflow? Can we somehow take the expertise from the computational science expert and embed that in an application and hide away the details and the tips and the tricks so that someone like me who doesn't have the background can run the simulation? And how do we enable stakeholders with a wide variety of expertise and backgrounds to actually use this modeling and simulation technology? So those are some of the questions we're asking in this work. And our answer revolves around the idea of micro workflows. All right, so I've already sort of stated the idea and just beat you over the head with it a little bit more. I'm trying to take this complex thing and make it simpler, right? That's the whole message of my story. And I'm going to show you a couple of ways you can do that and tell you about some tools that you can use to do that. But the main idea behind micro workflows is that we want to bundle these workflow components into small, complete applications where there's one place to go to carry out the whole workflow, from parts of pre-processing to the simulation execution to post-processing. We want to expose just those modeling and simulation capabilities that are necessary to run a predefined use case or experiment. This should enable analysts and stakeholders to jump right in and just get started running their simulations, and ultimately getting answers from them. We wanted to provide a way to define use cases and simulations, perhaps with something like a templating mechanism that a computational science engineer can use to create these much more simplified workflows. And the idea here, again, is just present only the configuration options that people who are using the simulation really care about. What does it look like to define a micro workflow? Well, step 1, you have a computational science engineer who knows the full simulation workflow, the physics behind it and everything, who works with stakeholders to formulate different use cases or simulation. Step 2, stakeholder and the computational science engineer will identify the relevant parameters that should be exposed that they care about, dials they want to tweak, settings they want to change. And then step 3, the computational science engineer takes that plan and works in some way to map those parameters that are exposed back to elements in the simulation input system, whether it's input deck or some other settings configuration mechanism. Finally, the software engineer, or maybe even the computational science engineer themselves, creates an application with some graphical user interface to facilitate the exploration of these different exposed parameters in the micro workflow. In our work, we have developed a system for creating templated micro workflows. So these just contain a few basic elements that are pretty simple to put together. Some are graphical, like a thumbnail that depicts what's being, some representative image of what's being simulated in this use case. Text summary, again, that is a little bit more descriptive of what is being simulated and why you might use it. Some tags for searching. So if you have hundreds of use cases, some way to refine which ones to bring up, some basic basically a search mechanism to find relevant use cases for the problem you're trying to solve. And there's some kind of form element where you define which parameters you're exposing. And here we have 3 parameters in a mixing problem: rotation speed, liquid level, dye injection time, and so on. And then the hard parts, mapping these values to the relevant values in whatever the input configuration system, the configuration system for the simulation code. And that's represented by input deck here. So it's really just a handful of elements to define these. Nothing terribly complicated. We'll get a bit more concrete picture coming up here when I do a talk about ArrowFlow. But this gives you an idea of how does the computational science engineer, how can they do some work in sort of a little bit of a generic micro workflow system, but let them really customize what science use cases they're exposing. Okay, so that brings us to our poll question number 2, focused on basically what is the most challenging part of setting up your simulation workflow. So let me bring that up here, poll 2, and I'm going to launch that. Give maybe 20 seconds or so. You can hopefully find all the options faster this time since you did it one other time.
I thought
Can
the
you see
CAD
that?
modeling was, yeah,
Yeah.
everyone can see it, and
Oh, okay.
it was interesting to see that the CAD modeling was really the clear winner, but now it's kind of like getting catch up by others.
Yeah. All right, we have 82% voted. Let's go a few more seconds here. Okay. And then share the results. So yeah, CAD modeling, number 1. Yep. We've done a little bit of that, and I can see why that's a challenge. Choosing the physics models is next. Defining the simulation inputs. Interesting. Not running the simulation is straightforward. Well, that's good. That's probably the first thing a simulation software producer wants to make sure it works really well is people can run it. And then understanding the results comes in at 30%. So, all right, thanks for that feedback. Very helpful. I'm going to close the poll, and I'll continue on. All right, so this is a little bit of an interlude slide, but the purpose of it is to talk about how we deliver kind of any application, but in particular a micro workflow application. So, I'm sure you're familiar with desktop applications. You go download them, install them, just use them on your desktop. That's pretty straightforward. But more and more, we're finding folks are interested in doing things through the web. So we can skip that installation step. Maybe you need your IT administrator to come install software. If you can just go to the web, there's a lot of appeal to that. And more, the web is becoming sort of a pseudo operating system for application delivery. Surely you've been using web applications that are quite capable and do just about anything a computer can do. So which might be more interesting for folks who are interested in simulation technologies and analyzing results, analyzing data, it might be the desire to embed one of these micro workflow applications into something like a Jupyter notebook, right? So you have this kind of nice predefined user interface where you could take the pre-processing and the simulation, the post-processing, but then you can embed it in sort of a more environment more suited to the curious and who also know something about NumPy or SciPy or Pandas maybe to grab the data results and then do some further analysis. So we've been working on technologies here that support all 3 of the application delivery mechanisms that are shown here. This particular application is called AirSans. It's for analysis, inspection, and reduction of this data produced by small angle neutron scattering instruments. So this is raw data. This isn't really in a simulation context, but it gives you a picture in your mind, at least, of what application and application delivery looks like. So we have a very cool platform technology called Trame, which I understand is a French word for framework. And Sebastian here, who introduced this talk, is one of the masterminds behind Trame. And, if you have questions for him, this is a great venue for that. But Trame is a Python package to build powerful visual computing applications like the one I just showed. And the cool part is you don't need any kind of web programming knowledge. You just need to know Python and some Python packages, and it helps if you want to do a 3D visual computing application to know something about the visualization toolkit and ParaView. But it lets you write Python applications that run on the web, in the Jupyter notebook like I showed, and there's even a way to embed these in desktop applications and distribute them in a more traditional fashion. Trame uses Vuetify by default for its graphical user interface, but there are ways to use other GUI layers if you're a more web-focused developer and have a different GUI system that you prefer to use. As I mentioned, it integrates, and this is one of its a really big strength, is it integrates with the visualization toolkit and ParaView and really any visualization toolkit-based application to provide easy to write interactive post-processing applications with 3D elements to do visualization on the web. And like our platforms that we mentioned at the beginning, Trame is licensed with a commercially friendly open source license, which means you can go download it, install it, use it in your applications at no cost or no licensing fee. There's some probably attribution term in the license just to say, hey, we use Trame, but other than that, it is a open source, and you can just take it and get started with it. Some of the benefits of open source software is obviously they're free to use. You benefit from developments that the community puts into future versions of the platform, and so you get bug fixes and enhancements sort of for free if you base your software on that. And it just really gives you a quick boost into your application process. There's a whole bunch of stuff that's been developed, and you can just use that and go and then put your special application features on top of all of that. And that's true for all the platforms, but particularly Trame here. If you want to find out more, there's a QR code in the upper right corner, and it will take you to a page with more information about Trame. So
before switching, can you go back? There's a questions of why just not a Python script rather than Jupyter component? That was kind of like your example between the desktop, the web UI, and then within Jupyter. I'll answer that question if you don't mind.
Yes, thank you.
So since most of those applications are based on Trame, and you get that for free between desktop, web, cloud, or Jupyter, technically it's not just a script, it's more like a library that we create. And then when you run that application, either you get the UI directly available to you, or in the context of Jupyter, what you do, you just instantiate the application object, and then you can just ask to get the UI and put it as a result in your cell output in the Jupyter. So it's technically a Python script, but we tend to bundle it more into a library, so you can have the freedom to just run it or instantiate it, ask a piece of the UI or the full UI, and have that available in your Jupyter piece. Most of what Corey was showing previously was a post-processing application, reading data and presenting the results, but Trame solutions can be anything from the pre-processing, running simulations, and so on. And in Jupyter, we've got other applications that let you like explore, interact with your data more easily. So yeah, it's a Python script, but it's definitely not a Jupyter component. It's just using a Trame web UI, and then we're just presenting it inside Jupyter. That's what it is. Keep going,
Great.
Corey.
Thanks, Seb.
You're welcome.
Yeah, so just a quick peek at the Trame application architecture. Trame takes care of a lot of details. That's how I like to think about it. There's a lot of technologies behind the scenes that it uses, WSLink, BTK.js, Node, and other things, but it really provides that way to write Python to produce web applications, but then it also takes care of a lot of the orchestration of the client-server communication between the web client and the server process running in the back end to exchange application states, handle events, show widgets and respond to widget actions in the UI, and so on. And because it's based on Python, you can use whatever Python tools that you want to use, different Python packages, SciPy, NumPy, Xarray, Dask, so on. The sky's really the limit. There are a couple of applications that showcase this integration of different Python packages with Trame. So the Explainable AI Toolkit on the left uses the PyTorch package. Visualizer in the middle uses the Trame Simput package for automatically generating the UI from information, basic meta information that's available in the ParaView application. And on the right is a VeraCore application, which uses VTK and Plotly.
We've got another question.
Yeah, great.
Sorry, can you go back? Someone was asking, is it possible to interface C++ with Trame? Because we kind of talked about Python so far, and
Yeah.
so we've done it before. Mainly, we do have to do or create a wrapping interface to the C++ code using Python. But some of our customers are actually creating their full engine in pure C++ and just exposing a few API that makes sense, and then rely on Trame to just connect their UI to that facade API that they've created in C++ and expose to Python. So we still need to go through Python. This is our kind of like glue bridge technology. But Python is very flexible to enable other languages and other solutions that are more like performance when you do visualization, data processing, and so on. That's why VTK is based on C++, and that's why it's also working in Trame. Sorry, keep going.
Great question. Yeah, great question. Great answer. Thank you. All right. Now we have a question for you. This is our last poll question. Which Python packages do you use for data analysis? I'll launch that here. Obviously, there are many, many more than this, but we can only put so many in the poll. I love watching the progress update here.
Yes, SciPy, NumPy, and Panda were the clear winner at the beginning,
Yeah.
but
Still holding strong.
yeah.
Got 64% voted.
People still use Matplotlib.
Oh yeah.
I prefer Plotly personally, but
Okay. 73% voting. Those are our results. So SciPy, NumPy, maybe no surprise there. Clear winners. Pandas, very nice percentage, 63%. And then Matplotlib and PyVista, which is built on top of VTK. That's great to know. And we've done some Trame PyVista integration work, right? Yeah.
Yep.
Cool. All right, I think I closed that poll. All right. And we'll continue on here. So that brings me to the part where we talk about a couple different applications that encapsulate the micro workflow idea and make it real concrete. The first is Peacock 2.0. This is a encapsulation of the entire Moose parallel computing framework. So Moose is a finite element analysis framework and set of solvers that you can use to do all kinds of different physics, including nuclear physics simulation. So here's a couple of screenshots of the overall application. So you'll see a theme in the next two applications where we go from input simulation to post-processing. Right? So here is definition of the input. We have an input domain here where boundary conditions can be set. Notice some GUI elements here. I apologize, it's a little bit of a low resolution image, but it gives you an idea of where things are in the application. This is for the problem setup. Sorry, okay. Next would be some additional setup. This is where you're setting more of the physics and other parameters for the simulation. So Moose, the developers have done a really good job in making input decks really tailored and boiled down to what engineers need to define. So this application is a little bit low on the side of reducing parameters to just a very small set. Really, the goal was kind of the opposite here, is make learning easier by exposing most of the parameters through a GUI, but also providing a side-by-side view between the GUI settings and what gets generated in the input deck. And that's what you see on the side on the right there. So this is a tool for ease of learning, and it was one of the things you can do in one of these micro workflow environments. So this is again on the input side of things. There is an execute panel here. We have buttons to run or kill the process, clear the output, some settings on the job execution itself. You get a console that produces output from the running simulation. In the end, you analyze and visualize the data. This is using ParaView to generate some isosurfaces, this grid axis here, and some clipping of the data set. Notice that there are some parameters exposed for the visualization that you can fine tune to adjust what you see here. But again, this is, we went from pre-processing, setting up the simulation input deck, to execution, to post-processing, all in one interface that's compact, one place, easy to use. Next, I'm going to talk about Kitware's ArrowFlow application.
Sorry.
Yeah.
Sorry, we've got a question on, I guess, on the Peacock. Someone
Perfect.
is wondering if there's some parametric studies, or is it possible to perform some parametric studies using Peacock? So in the current UI, not exactly. We just provide one parameter at a time. But depending on how we create our application or the micro workflow that we built around Trame, we can generate such a system that will trigger many simulations and let you navigate through the results. And later on, Corey will present ArrowFlow. And while the current UI doesn't give you the way to define those parameter studies, we do have the results page that lets you pick the various simulations and possibly compare across various parameters as well.
Yeah, and we'll see that in a minute here. But yeah, that's a logical feature to want to add into a micro workflow application, right? So yeah, now turn our attention to ArrowFlow, and we have a demo of ArrowFlow in a minute here. But this is an application developed in collaboration with MStar CFD. It's a way to interface with their GPU accelerated solver. You see on the right here a couple of example use cases. Those are defined with that templating idea that I talked about, and we'll make a little bit more concrete here. And right now we have customers in the personal care products and pharmaceutical industries using ArrowFlow to broaden access to modeling and simulation across their enterprise. What does ArrowFlow look like from the stakeholder or non-simulation expert? Well, in step one, you pick your use case, which we've seen a few times before here. Two, you set up the few exposed parameters on that use case, and then run it and analyze the results. So this GPU-based solver for smaller models will produce output rather quickly, so you can watch the simulation evolve in real time. And as new time steps are available, we see the updated result in the interface. So you can use this to get really quick feedback and testing out different sets of parameters in the model. From the computational science engineer point of view, there's just a couple of things to set up to define each of those use cases. So you have to do a little bit of CAD-like modeling in the MSTAR pre-application that comes with MSTAR CFD, and that produces an MSB file that is part of the case file, or part of this use case. Come up with a nice picture and a summary text. And then the real work is in defining a couple small text files. There's a JSON text file that says what are the default parameters that we want to show in the interface when someone first loads it up. There is a GUI template that you use to define the different GUI elements. It's a little bit specialized, comes from Vuetify, but it's not hard to learn, and it's in an XML type format. You can do things like set minimum and maximum values, how many steps between those values, typical things you would see in some kind of graphical user interface framework. And finally, there's a mapping file that maps values coming from the form back to the larger input system that MSTAR uses. So there's really not that much to set up once you've figured out what properties you want to expose and once you've created your initial geometry using MSTAR pre. So at this point, I'm going to switch over to a live demo. So here
so while
is...
you're switching, I thought you will take more longer. There's a questions. Let me answer that, and then I let you. So there's a question about the managing of the workflow and dependencies. Is it Trame? Is it another library that deals with that, and so on? Well, the way we've approached that solution is Trame is really about connecting the UI and your core application on the back end using Python. In the ArrowFlow cases, our workflow is very well defined. So it's kind of baked into the application itself, or the logic that we've defined. Same thing with Peacock. We have the input tech definitions we need to run, and then we do the post-processing. For more complex dependencies and so on, or task management, we can rely on a third-party Python library that could describe that. So either it could be directly done at the application level because of what we are targeting, or if the application aims to be broader or more generic, then we can bring up other dependencies, managers, or workflow executions system that Python has available. But yeah, in ArrowFlow, that's directly baked into the application itself. Go ahead.
Great question. Yep. So here I'm going to pick one of the use cases. The one I know best is agitated tink. It's used to predict blend time, pre-surface motion, and mean fluid shear in a particular kind of tank at some fictional manufacturing plant somewhere. And once I confirm I want to use this, then I will click on the simulation tab. This is where I can set those few exposed parameters. I could run the simulation. It takes about a minute or two to get started, so I'm not going to do that. Instead, I'm going to load a pre-existing run. So we've saved the results, and we see that in this configuration of parameters, we already have an existing run, so we don't actually need to use the resources to run the simulation or wait. We can just look at what's available here. So we start out with a 3D visualization of the output. Now this is all rendering in my browser frames that are generated on a server sitting over by Seb, I think across the country. I'm in North Carolina, he's in New Mexico, and we get pretty good responsive 3D application. There's not a whole lot of lag. There's a little bit, but it's not too bad. There's some compression artifacts, but it looks pretty good. So this is a time evolution, and I'm going to run that and adjust the color map so that we can see velocity on this kind of semi-transparent cutting plane, and we see the animation going. I'm going to just pause that here. You can control different visibility of different elements and then their relative opacity in the scene. We can change the variables that we're showing on the slice plane as well. I'm going to put this back to velocity. Then we can also plot different quantities of interest here. So things like moving body power, the volume fraction standard deviation, the scalar die over time. And notice as I move the time scrubber, the vertical line, dashed red line here, shows us where we are in time. So it's very interactive, and there are some other plots that we can show here, things like the cumulative volume fraction, overall volume fraction, and so on. One cool thing here is that for any given use case, we can generate a QR code. So imagine a field engineer is trying to figure out how fast to run a mixer in a tank, and they're out in the field. They could scan this QR code that's maybe printed out and put on the agitator tank that they have out in the field, and they'll bring them to this kind of simulation, and they could set those settings to what they are thinking about using, run the simulation, get sort of immediate feedback, and then maybe make an adjustment out in the production. So, sorry, I'm jumping back here. In the end, we can see a list of results that we've already generated. So these were already run. The simulation has run, and these are the different configuration settings. So we could load any of those and view them, delete them if we're not interested in any of them or in them any longer, and so on. So, Seb, am I missing anything to show? Those are the highlights of the feature.
The results page, I don't know if you've seen it. If you go back,
huh?
The third tab, basically, like where you have all the parameters,
yeah.
so you can like load them. But like you saw before, when you are changing those sliders, you can actually get, you know, when the simulation with those parameters has already been run. But no, I think you covered it. One thing I did while you shared the QR code is I took my phone and showed that I was connecting to the same simulation with the same results. So the QR code can be provided at different stage. So if there's a specific results with specific RPMs and die injection time and so on, you can have a specific QR code there. Or if it's just for the agitated tank simulation template that you want, you have a different QR code, and then people can just go there, like you were mentioning.
All right. So this would be, yeah. So if you want to start a new one, this is the one you would go to. Yeah.
Yeah.
But if you had specific results, and
the one you shared earlier, I was directly connecting to the same result as you. When
I understood. Okay, great. Thanks for clarifying that. Okay. So that ends the demo of ArrowFlow. So we'll jump back here, just a couple of slides left here. And so we'll just cover some advantages to micro-workflows. So as we saw, we can increase the ease of learning, like in the Peacock 2.0 case, so ease of use, like we just saw with ArrowFlow, of simulation workflows. Computational science engineers can focus on the scientific formulation of the problem at the request of the stakeholder instead of doing some of the grunt work of actually running the simulation and collecting the results and presenting them back to the stakeholders. And then the stakeholder can just concentrate on the solution they're trying to find and not in learning how to set up the simulation and run it. Right. So we expect, or with those advantages, we are making advanced simulation tools more accessible and hopefully more impactful. As for our outlook and future directions, we're seeing a lot of interest in providing micro workflows to our industrial, academic, and government customers. So we expect that the growth of micro workflows will continue. And we hope that as a result, the cost benefit ratio of deploying these modeling and simulation tools will just improve as more and more people can use the technology directly. So I invite you to try ArrowFlow. Our demo is up to date. Follow the QR code. Sorry, this URL is not where the demo is that I just showed you, but the QR code should take you to arrowflow.tram.kitware.com. And in terms of next steps, if you are interested in learning more, you can get started with Trame at tram.kitware.com. There's a discussion board for Trame on GitHub where development occurs. There's a technical page, more technical page available linked off of there. We have a Trame course given by Seb himself coming up on May 6th this year, so just around the corner. So you could sign up for that to learn more. Of course, Kitware offers paid support, contract services to help you with all kinds of things, from learning to implementing to developing full applications for you. So we offer software customization services towards that end, where we can include your branding, add new features, define custom workflows, and so on. So if you have general inquiries about that, please reach out to us at kitware.com/contact, or email kitware@kitware.com to get a hold of us. So that
Corey,
ends my, yeah.
we've got plenty of questions. I
Oh, great.
hard time keeping up.
Okay,
But,
so perfect timing. It's Q&A. So
okay, so you compellingly demonstrated the benefits of workflow, but it's not clear to me what part of this is micro, what portion of the workflow can be transplanted to other workflow for reuse. How reusable are the various pieces from simulation to simulations and from framework to framework? So I'll try to take a stab and maybe I will miss something. The micro part is really driven because of the laser focused goal of whatever we are doing. The great example of a micro workflow, at least the way we see it, is ArrowFlow, where the workflow in question is you pick a template, you define parameters, you run and see the simulation at the same times, and then you can like extract the information you care about with the post-processing tool that has been like integrated into the systems with no extra parameters or extra filters or things like that. Like we've already curated all the processing, and the templating infrastructure is already curating the simulation itself. So the application as it's as a whole is basically taking a step of defining what is one workflow for many types of simulation for in that CFD realm, I would say. Corey, I don't know if you want to add anything on that part for the micro part.
yeah, I think you captured that pretty succinctly. But yeah, there's an inherent conflict between the focused nature, focusing on one type of simulation and trying to transport to another. Templating mechanism can be defined within one kind of simulation framework and be reused. Once that's developed, you can use that to do a lot within a particular simulation software and post-processing setup.
And for the question, what portion of the workflow can be transplanted to other workflow for reuse? With Trame, we kind of go with the component approach. So if you created an application for a specific use case, and you have a different workflow, but you really like the post-processing of one or the input deck of another, then you can start reassembling those pieces specifically for that other workflows. There's no like magic bullet that will solve everything at once, but at least when you start building those pieces and those applications, since it's just a Python and not necessarily just a Python script, but more a library, you can start like importing those library and bringing those pieces into other applications and create more complex components. We technically have, we are currently working on solutions for ParaView to enable higher components infrastructure for ParaView, so you can build up your ParaView in a web way and defining what you want to have and what you want to enable. And with workflow, we kind of see the same pattern that could be applicable. We just need to make more and more of those applications to really cover the base there. Yeah, and for the last question, how reusable are the various pieces from simulation to simulation, from workflow to work, from framework to framework? Well, if you work on HPC and you already developed a Slurm queuing system, monitoring, submitting thing, you can reuse that piece across your environment. Same thing for the post-processing, same thing for the input deck. Maybe it's you have like various implementation of the input deck definition. Like in Peacock, you can see that we were using Simput to get the UI generations and with the help and so on. But we also use a VS Code types of component that let you directly see and edit the raw input deck definitions. And in fact, when you enable the language systems in Peacock, you even have like tooltips and information when you're typing to know what are the options and what are the domains available within that component. And that same component, VS Code, can be used for another applications and other solutions. So let me see. What did I answer? What I did not?
I think we're up to the top two are left.
Okay. Do you have a simple tutorial on how to map a simple micro workflow in Trame? Trame Simput does provide some example on how to use the generative UI based on some model that you need. But the problem with micro workflow or simulation is like each of them are unique in many ways. So I don't think we've got a generic enough tutorial to say this is how you do all the steps. But all the pieces are described in the various relations to Trame. The other question is the orchestration of core app functionality in the micro workflow simpler to debug because it's hiding behind and integrating cross-platform library.
Right. So I think that's is the orchestration of core app functionality in the micro workflow simpler to debug because it is that orchestration is hiding behind integrated cross-platform libraries. Not,
I'm
yeah,
not
I'm not
sure
sure it
to
would be.
understand.
I don't know if it'd be easier to debug because of its nature, but certainly you could develop it before putting it out to the users and sort of hide that complexity from them at least.
Yeah, I guess my take is really
Yeah.
about if you focus on a tiny problem, then you don't have to worry about all the capability of your solver, all the cross not working options that you have in your various environments. So it's really about narrow it down. And I guess with Trame, I feel that building another app when you already built something very similar really takes almost no time. rather than creating something very generic where you have to make sure every use case is taken care of and tend to kind of increase the complexity of your code.
Second question in that section is, what are the disadvantages relying on efficient application delivery mechanism through micro workflows? Yeah, I suppose maybe if you're making it simple for people to use and they use it sort of carelessly, I guess you could be using more computational resources than you intended to. Kind of a human problem, I think, to run simulations that you really need to know the answer to. I guess that's one I can think of. Hopefully it's not too much of a problem. Anything to add to that, Seb?
No, sorry.
Okay. And last one is also, what environments will work best for micro workflows? So I'm going to interpret that as maybe computational environments, maybe the HPC versus running on the desktop versus cloud, something like that. Is there any one of those that is better for micro workflows than others? I guess my answer would be some of those require more elements in the workflow. So if you're running simulations on an HPC system, there's some kind of probably job submission, coordination you have to do with that in the micro workflow. The data movement, do you have access to the file system where the data resides from your the server that serves up the application? Those can add complications, I think, to the micro workflow setup. If you're running everything on your desktop, it's all on one disk and one system. That's probably the easiest way to deploy and design and deploy a micro workflow.
Well, I would add to that, Corey, that with Trame, like if you submit or if you work on HPC, you can run your Trame process on that HPC, so it's still kind of your desktop usage, except that you are on the HPC, and then those HPC don't tend to have UI, and with Trame, with the web interface, you can easily kind of just connect or forward the network connection using your browser and directly drive the parameters, the visualization, the post-processing on the HPC directly. And so far, we've got a couple of deployments of people using it on HPC and finding like benefits there.
Okay, I think I went through all the questions. I think we answered them all. Thank you, everybody, for attending, or in the future, watching, if you're watching the recording of this. We really appreciate your time.
Thank you, everyone. Have a great day.